So now we're going to be having a look at the Poisson distribution. So this is a different distribution. In AS we had a look at the binomial and the normal distribution, and now we're going to be having a look at the Poisson distribution. So the Poisson distribution is similar to the binomial distribution. In fact, they are both for discrete distributions. So if you remember, the binomial distribution can only take on whole number values, and that is the same with the Poisson distribution. And also, just like in the binomial distribution, there is certain criteria that need to be met in order for us to perform a Poisson distribution, or to be able to say that our data can be modelled using a Poisson distribution. So the events must occur individually in time and space. So if you are counting the cars that pass a point in a road, it must not be possible for two cars to go past at once. So for instance, you can't have two lanes, it must be a single lane road in order for that to happen. Also, the events must happen at a constant average rate. So for instance, the number of phone calls that you receive per half hour must be the same in any half hour that we're looking at, for instance in the morning or the afternoon. The events must also be independent of each other, which means that the number of customers coming into the shop have to come in by themselves and not in groups. So it's not that one person's going in because another person's going in. People have to be going in on their own. And also, there must be no upper limit to the number of events that can occur. And this is the key difference between Poisson and binomial. If you remember, binomial, we had a set number of trials, whereas with Poisson, we have no upper limit, which means that we have to continue to be able to count. This time, our distribution is written as X squiggle PO for Poisson. Again, it's the letters in the word, okay, the letters in the name of the distribution, so it's quite easy to remember. And this lambda symbol here is the mean and the variance of our distribution. So that's here. The lambda represents both the mean and the variance of the distribution, and it can also be known as the parameter at times. So this also has an extra name, which is called the parameter. So lambda is also known as the parameter. So sometimes you'll see that word parameter, and that is meaning the mean and variance. And that gives us another thing that we need in order for the Poisson distribution to fit, and this is usually the one that we are testing, because the other ones we can't really test unless we know exactly what's going on in the experiment. But from the data that we have, we can check if the mean is close to or the same as the variance of the distribution. As the Poisson distribution is discrete, we are going to be having a look at Ppd for when we're looking at the probability that it equals an exact value, and Pcd for when it's less than or equal to a value. And again, in the same way as we had with the binomial distribution, if you have one of these nice fancy new calculators, we're just going to have a look at what that looks like for Pcd at the minute. So if you're going to dist, and then we have to go across this time, so using this arrow with F6, and then it says Poisson, Pcd, you can see that again we have a lower and an upper option. However, if you have one of these older forms of calculator, when you go into statistics, distribution, across, again this is Poisson, it almost says Poisson, you can tell what it's meant to be saying, and then we go into Pcd. If we change that to variable, you can see that again, in the same ways that we had for binomial, you just have x and mu instead of having lower, upper. So here we have lower, upper and lambda. In the older versions of the calculator, you have x and mu. So as we were just explaining, lambda is the parameter, which is the mean. So the mu in this calculator is the same as the lambda in this calculator. And in the same way as we did with binomial, the lower and the upper are inclusive. So if we have a look at the numbers that I just randomly already have in this calculator, this is looking at 1 is less than or equal to x is less than or equal to 5. Whereas in this calculator, the old calculators, you can only have a look at less than or equal to's. And you have to make the same adjustments as you would with binomial. So just as a quick recap as to what that would look like, if we had the probability that x was strictly bigger than 5 in this old calculator, that would be the same as 1 minus the probability of x being less than or equal to 5. If you had the probability that x was greater than or equal to 5, that would be 1 minus the probability of x being less than or equal to 4. So you're always trying to change it so that you have less than or equal to's in what you are putting into the calculator if you have one of these older models. That applies to both of the calculators if we have a probability of x being less than, let's say 5 again, because that is a strict inequality, not an inclusive inequality, so it's not less than or equal to 5, so we're not actually wanting to count 5 in there. That means that regardless of which calculator you have, we're going to be having to change it to the probability of x being less than or equal to 4. And it's very important that you remember this when you're trying to find the probabilities, and we're going to look more at that now. And remembering, as I've already said, we're going to be using Ppd for when it's an exact probability that we're looking for, so the probability that x equals something, and we're going to be using Pcd for our cumulative probabilities. So for this first question here, I'm going to start off with the new version of the calculator. We have a basketball player scores an average number of free throws in a game per game of 6. So that distribution can be written as x squiggle PO 6. And we're asked what is the probability that the player makes exactly 3 free throws in a game. So we're looking at the probability that x equals 3. So that's an exact probability that we're trying to find. So we need to go into dist, across to Poisson, and this is going to be a Ppd. So we go into Ppd, and in a similar form to what we have in this calculator, if I go back, dist across Poisson Ppd, here it's x and mu, here it's x and lambda, but again, as I've already explained, lambda and mu are the same value, and that's this 6 here. So our lambda is 6, and our x, the number that we're looking at, is 3. And that gives us 0.0892. And you should get that value regardless of which calculator you have. I'd now like you to pause the video briefly to give the Now You Try question a go. So hopefully you paused the video and you gave the Now You Try question a go. This time we have an archer who usually hits the bullseye 2 times during an archering session. So we've got x squiggle PO 2. What is the probability that the archer will hit the bullseye exactly 3 times during the session? So x equals 3, and as you can see we end up with this probability here, which to 3 significant figures rounds to 0.180. So continuing on from this, we've got a school estimates that 4 pupils per course will fail the final exam. So that's x squiggle PO 4, and this is talking about failing. The probability that fewer than 2 students will fail a particular course. So that's looking at the probability that x is less than 2. And like I said, regardless of which calculator you have, we have to change this to the probability of x being less than or equal to 2. So for the new calculator, dist across Poisson Pcd, because we're talking about the number of times that something can happen, well, the smallest number of times that something can happen is 0. So if we have no lower bound that's given to us, we put 0. The most that we're looking at is 2, and our lambda is 4, and that should give us 0.2 0.38 to 3 significant figures. If you have one of these older calculators, again, dist across Poisson Pcd, this time we only have an x and a mu option, so the x is going to be the 2 from here, and the mu, remember that's the same as lambda, is going to be 4, and you can see again we get 0.238 again. Having a look at the next example, and then I'll give you time to try the now you tries at the end. We have, according to recent data, the low-cost airline Ryanair loses passengers' luggage on average of 3 per flight. So that's X squiggle PO 3, and that is that they lose, in the luggage. We're trying to find the probability that they lose more than 4 pieces of luggage on a particular flight. So in this case, we have the probability of X being more than 4. Well, if you have one of these newer calculators, you can just change this to the probability of X being greater than or equal to 5. If you struggle with that change here, remember that if you think about a number line, this time we don't have an upper limit to our number line, so it will just go on forever. If we're looking at strictly more than 4, then we're looking at these numbers here, which is the same as greater than or equal to 5. And in that case, back in PCD, the lowest value that we want is 5. And because we have no upper limit, that means that the biggest value it's going to be is 99999999999, lots of 9s. Really big positive number. Our lambda is 3. And that gives us 0.185 to 3 significant figures. However, if you do have one of these old versions of the calculator, because we want everything to be changed so that we have a less than or equal to, instead of changing it to greater than or equal to 5, we are going to change it into, we're going to change it into 1 minus the probability of X being less than or equal to 4. And again, having a look at the number line, because we're talking about probabilities, the whole probability of this is going to be 1. However, I only want that red section there, so I need to take off this 0, 1, 2, 3, 4 that hasn't been included. So I need to do 1 minus the probability of X being less than or equal to 4. That I can now put into my calculator because the X is going to be 4. That's what the less than or equal to part is. My mean, my lambda, is 3. And that gives me now 1 minus 0.81526324. And again, because I am doing a takeaway here, I have given it to more significant figures. Then if we go back into the normal part of our calculator, we can now do that subtraction. So 1 minus 0.81526324. Just double checking that I've typed that incorrectly. I think I have. So that gives us to 3 significant figures, 0.185 even. So you can see there that you do end up with the same answer, it's just that you have to go about it a bit differently depending on which calculator you have. So I'd now like you to try these 2 now you try questions. So hopefully you paused the video and you gave the 2 now you try questions a go. For the first one, where again we were talking about people failing the exams, we were looking at then the probability that 4 or fewer students failed a particular course. So again, straight away that's simple to put in both calculators. If you have the newer version like this one on the left hand side here, then your lower is going to be 0, your upper is going to be 4, and your lambda is going to be 4, and that should give you 0.629. If you have the older version of the calculator, in PCD, our X is going to be 4, our mu is going to be 4, and that should give us the exact same value, which it does there. For the second question, which is about losing luggage, if we're looking at the probability that they lose less than 1 piece of luggage on a particular flight, Well, if they're losing less than 1, then the only value that there is left is 0. So that's actually changing it into a Ppd question, where regardless of which calculator you're using, your x is going to be 0, and your lambda or your mu, your mean or your parameter, whichever one it's asking for in your calculator, is still going to be 3 from our distribution here, which should give you 0.0498. So something else that's important when we're finding these probabilities is that the way that the information is given to us in terms of this constant average rate, our lambda or our mu, whatever you're wanting to think of it as, has to be over a set period of time. So here, when we are trying to find the Poisson probabilities, we have to know the average number of occurrences in a set time frame. And that's what we've been looking at without really thinking about it so far. So if that time frame changes, which quite often they like to do to make sure that you're reading the question fully, then we need to adjust our average number of occurrences to correspond to the new time frame. So we're going to have a look at how we do that. So here we have the number of accidents in a week on a stretch of road is known to follow the Poisson distribution with a parameter of 2.1. So remember, the parameter is just the mean, which is the lambda. So that's going to be x squiggle PO 2.1 as our original distribution, and that is looking at in a week. So I'm just going to write there that in this case my x is representing a week to remind myself of that time frame. So first of all, find the probability that in a given week there is 1 accident. So that's just a straightforward, using what we have here, 1 accident. So it doesn't matter which calculator you use, just going to use this one because I've got it up. Poisson Ppd, our x is 1, our lambda or our mu is 2.1. Whoops. And that gives us 0.257. It doesn't matter which one you use, whether you use that calculator or that calculator. Just quickly show it you again. Poisson Ppd 1 with a parameter of 2.1. Whoops, there we go, 0.257 again. So then, part B, we're now looking in a 2-week period that there are 2 accidents. So we're wanting to extend our x squiggle PO. Instead of it being for 1 week, we're going to have it for 2 weeks. Because it's a constant average rate that these accidents are occurring at, because our time frame is doubling, our parameter is just doubling as well. So instead of 2.1, which we had before, here, for 1 week, we're going to double that to now have a parameter of 4.2. Then we're looking 2 weeks, there are 2 accidents, that's looking at the probability of x equaling 2. So this time our x is 2 and our parameter is 4.2. And that gives us 0.132. And again, it doesn't matter which calculator you put that into, just whichever one you have. So there is a difference between how that's being asked and how part C is being asked. So part C is asking, what's the probability that there is 1 accident in each week of 2 successive weeks? Now that is different to 2 weeks where there are 2 accidents, because the 2 weeks where there are 2 accidents, you could have both of the accidents in the first week or both of the accidents in the second week, or you could have 1 accident in both weeks. So there are more different ways that those 2 accidents can occur looking at the way that part B works. However, the way that part C works is that we have to have 1 accident in the first week and we have to have 1 accident in the second week. And that means that it's only one of the 3 different situations that I outlined for part B that we're actually looking into. So straight away, I'm thinking that part C is going to be a smaller probability. And the way that we find this probability is going back to how we did probability in AS. We want the probability that we have one accident in the first week, and so we want the probability that we only have one accident again in the second week. Now luckily we already found the answer to this in part 1, which was 0.25715849. Notice again, because I am doing a further calculation with it, I have wrote the whole number down here, times again 0.25718515849. So if I go into the normal part of my calculator, so that's 0.257154849 times 0.257154849. Double check that we've typed that in correctly. 0.2715849 times 0.2715849. And again, anybody who's quite good at maths can see that that's the same as squaring the number. So I could have just wrote the number in once and then used the squared key, which is this one here. It's in the same place on both calculators, this button here. So that ends up giving me 0.0661 to 3 significant figures now. So as I suspected, this probability is smaller because, as I said, in part B, when it was just 2 accidents in 2 weeks, you could have both the accidents in the first week or both the accidents in the last week, or you could have 1 accident in each week to get the 2 accidents in 2 weeks. Whereas C is only looking at that last situation where there's 1 accident in each of the weeks, so it is going to give us a smaller probability. So I'd now like you to pause the video and give the Now You Try question a go, making sure that you're very careful about what the length is when you're giving it in the question and any alterations that you're having to make to that for part B, C as well. Okay, so hopefully you paused the video and you gave these 3 Now You Try parts of the question a go. So the first bit of information that we're given is that the number of flaws in a metre length of dress material is known to follow a Poisson distribution with a parameter of 0.4. So that means that we're starting off with x squiggle PO 0.4, and that is 1 metre. So for part A, we're trying to find the probability that there are no flaws in 1 metre. So for this one, we're not having to change our parameter at all. We're just looking at the probability that x equals 0, so we're using Ppd, and that should give us 0.670 to 3 significant figures. For part B, we're looking at the probability that there is 1 flaw in a 3 metre length. So this time, the length of material that we're looking at is timesing by 3, which means that our parameter has to times by 3. So instead of 0.4, we now have 1.2, and we're looking at the probability that x equals 1, which should give us 0.361. And then in the last part, in part C, we're looking at the probability that there is 1 flaw in half a metre length. So in the same way as we can increase going outwards, we can also decrease. So instead of 1 metre, we now have half a metre. So we're halving that original 0.4 parameter to give us a parameter of 0.2. And again in Ppd, as we're looking for an exact probability, we're looking at the probability that x equals 1, which should give us 0.164. And you can still see that one in my calculator on the left there. So next time we're going to have a look at how we can combine 2 different Poisson distributions together and in what situations it is appropriate to do that. Thank you very much for listening.